In this video here, we're going to take a look at early and late event times. Now, the activities within a project typically take different lengths of time to complete. So the length of time an activity takes to complete is known as its duration. What we can do then is we can add the weights to the arcs in an activity network to represent these times. And you should also be aware here that each node or vertex, whichever you prefer to call it, of the network represents an event. And it's useful to consider two separate times associated with each event. So to get us started here then, we have the early event time. Now the early event time is the earliest time of arrival at the event, allowing for the completion of all preceding activities. And we've also got the late event time here. So the late event time is the latest time that the event can be left without extending the time needed for the project. Now the diagram below demonstrates the way that we present this information. So what I've got here is my activity, right? Activity A. And this number inside the bracket next to the denoted activity, this here is the duration. So this here is the duration. Now these boxes here, we use these boxes to represent the early event time and also the late event time. So the top box here, this box on top, this is the early event time. So early event time. And then the box underneath here, that's this box here, this is the late event time. Okay, so that's everything for this page here. We also need to learn about something called a forward pass or a forward scan, whichever name you prefer, and also a backward pass or a backward scan, again, whichever name you prefer. So let's just take a look at that on the next page. Now, the early event times are calculated starting from 0 at the source node and working towards the sink node, and we call this a forward pass or a forward scan. And the late event times are calculated starting from the sink node and working backwards towards the source node, and we call this a backward pass or a backward scan. And just so you're aware as well here, you can use either of these names interchangeably. Now, what I've also got on the screen here is an example of an activity network. And you might recognize this activity network here. It has popped up quite a bit on the previous few videos within this chapter on critical path analysis. Now, what is different here is I've replaced the nodes with the early event times, right? Don't forget then, the top box here is the early event time, and the bottom box here is the late event time. And what you can see then is I've already filled out the early event times for each event here, okay? Now, let's just quickly run through this. So, to begin with here, the first thing to mention is for the early event times, we always choose the largest number, okay? That'll become clear as we work through the activity network in a short while. I'll explain that in more detail. And then for the late event times here, we always want to choose the smallest possible number. And again, I'll explain that in more detail as I work through the activity network in a short while, okay? As we mentioned before, the number inside the bracket here next to our activity, this number here is the duration of that activity. So for example then, activity A here has duration 3, activity B has duration 2, activity C has duration 2 as well, so on and so on, okay? Now, as I've already mentioned here, as we can see then by this diagram, right? I've already filled out all of the early event times, but let me just briefly explain how I obtained all of these values. So for the first value here, in fact, before I go on to this one, the first thing to mention here is at the source node here, our first event, it always starts as 0. Okay, so we always start with 0 here. Now for this event here, we consider what activities are going into this event. Well, there's only one possible option here, right? That is just activity A with a duration of 3. So the largest possible choice then is just simply 3. And the same applies with this event here. There's only activity B going into this event here. So my only choice then is 2, okay? So moving on then, this event here is a little bit more interesting because I've got a choice of 2 activities here, right? I've got activity C with a duration of 2 and activity E here with a duration of 4. So for this 6 here, I'm going to make a quick note here. So for activity, sorry, not activity, for this event here, I'm just going to get rid of that arrow. It's not very clear. Try again. In fact, let me do it in a different color. Do it in red here. So for the 6 here, okay, we'll do it in red. What I want to do then is choose the largest possible number here. So largest of them. So I've got a choice of 2 here. It's either going to be 3 plus the duration, which is 2. So 3 plus 2. Or it'll be 2 plus the duration, which is 4. So 2 plus 4. Now clearly, 2 plus 4 is larger than 3 plus 2. So we choose 2 plus 4. And that's where we obtain this 6 from here for the early event time. Okay? Again, for this event here, or this node here, I've got a choice of 2, right? So it's either going to be, again, I'll make a note here, the largest of, so I've got a choice of 3 plus 6, so 3 plus 6, or 6 plus 2. Okay? Now clearly, 3 plus 6 is larger than 6 plus 2, so we choose 3 plus 6, and again, that's where we obtain this 9 from here. And then finally, for the very last node here, or my very last event here, this 10 should hopefully be quite obvious, right? We've only got one activity G going into this event here, so in that case then, it's just going to simply be 9 plus 1, giving us 10 there, okay? So that's where we obtain all of the early event times, but what about the late event times here? So, as we mentioned before, we work backwards here from the sync node, okay? So we start from the sync node and work backwards towards the source node. Now, the first thing to mention here is the early event time always becomes the late event time at the sync node. So whatever the top number is here, it's the same for the bottom number. So because my top number here, the early event time is 10, my late event time is also 10. I also put a 10 down here, like so. We now work backwards. So going backwards here, we do 10 minus 1. So notice before, as we worked forwards, we added. Working backwards now, we subtract here, okay? So I want the smallest of the one possible thing here, which is just simply 10 minus 1. That gives me 9 there, okay? We put a 9 like so. That is supposed to be a 9. I appreciate it's not very clear. Let me just try that again. Oops. So this is a 9. There we go. That's a little bit better. Perfect. So again, we just keep working backwards here. So clearly I need a late event time here for each event, right? Or each node. So going backwards here, we've only got one thing going backwards, right? So it's just going to simply be the smallest of just the one thing, which is just simply 9 minus 2. So my late event time here is just simply 7, okay? Now, this late event time here is a little bit more interesting because I've got a choice of 2 here. So I want the smallest then. And again, let me just do this in a different color. Let's just do it in dark blue here, okay? So I want the smallest here. So the smallest of, so I've got a choice here. It's either going to be 9 minus 6. So it's going to be 9 minus 6, like so. Or my other choice here then will be 7 minus 2, right? It's the smallest of 9 minus 6 or 7 minus 2, okay? Well, clearly, 9 minus 6 is smaller than 7 minus 2, so that's 3, that's 5. So put 3 there, okay? I'll just do it in the same color anyway, it doesn't really matter too much, like so. Going backwards here, again, I've got a choice of 2, so let me just fill out this one here, this node here, or this event. So it's just going to simply be, at this point here, the smallest of the one possible option here, which in this case here would just be simply 7 minus 4. That would just give me 3 there, okay? So it's just the one choice there. And then going backwards here, I want the smallest of either 3 minus 3, which is 0, or 3 minus 2, which would give me 1, right? So clearly, I'm going to choose 0 there. That is the smaller of the 2 choices there, okay? So The late event time at the source node is always 0, as we've just filled out there. And the early event time always becomes the late event time at the sync node, which we've already mentioned at the beginning of filling out the activity network. But again, just so you're aware. Okay. So there we have it then for this introduction here to early and late event times. Hopefully this has helped. And as always, I think the best way to really demonstrate this concept is just work through one practice question. So let's just get started then with this practice question. So let's just get started here then with this practice question. Now, as we can see then for this question here, we're told that the activity network for a project is given below. And we can see that here then from our diagram. We're then told that the number in brackets gives the time in days to complete each activity. So, for example, then activity A here would take 4 days to complete. Activity B would take 7 days to complete. Activity D would take 5 days to complete, so on and so on. You get the idea. So all we want to do here then is just find the early and late event times at each vertex. Now, where do we begin then? So we always start from the source node here. That's the first vertex, and that always starts with 0. 0, so an early event time of 0 and also a late event time of 0. And to begin with here, we implement a forward pass. So we start from the source node here and we work forward towards the sync node here, the final vertex. And in a forward pass, what we're actually finding here is the early event time for each vertex. Okay, so let's just start from the source node here and see if we can find the early event time for each vertex. Now, to get us started here, you might think to start with this activity here for this node. But the issue here then is we have this dashed line, right? Don't forget then a dashed line here indicates a dummy activity. And obviously a dummy activity has no value, but we do still need to consider that when we look to find the early and late event times at each vertex. Okay, so let's just start with this vertex here. So I've only got a choice of one thing here. So don't forget then, in a forward pass, we always want the largest possible option, but I've only got one thing to actually consider here. That's just 7, right? So the early event time then for this node here or this vertex is just simply 7. Perfect. We can now find the early event time for this node here or this vertex here. So I've got a choice of 2, right? Let's just make a note here. So I want the largest then of, so largest of here. So like we just said, we've got a choice of 2. It's either going to be 0 plus 4. So 0 plus 4 or 7 plus 0. And clearly 7 is greater than 4. So my early event time here is 7. Don't forget, we always choose the largest here as we go forward. So let's just keep going here. Now, currently, I can't find the early event time for this node here because I don't know the value of this early event time here. So what I need to do now is find the early event time for this node here. So again, I've got a choice of 2, right? So I'm going to be 7 plus 5 or 7 plus 4. Don't forget though, we always choose the largest. So we choose 12 there as the early event time. Perfect. So we can now find the early event time for this node here. Again, I've got a choice of 2. So I'll make a note here. So again, largest of. So my choice here is 7 plus 2. So 7 plus 2 or 12 plus 0. And clearly 12 is greater than 9, so we choose 12 as the early event time there. Now for this one here, I've got a choice of 3, right? So my choices are 12 plus 3, which would give us 15, 12 plus 4, which would give us 16, or 7 plus 5, again, giving us 12. So clearly, we choose 12 plus 4, so that's 16, as the early event time. Now for this one here, I've got a choice of 2 again. It's either going to be 7 plus 4, which is 11, or 16 plus 0, giving us 16. So again, we choose the larger option there, which is 16. And then finally here, for the final early event time here, I've got a choice of 3 again. So I'll make a note here. So largest of. So what are my choices here? So I've got 12 plus 10. So 12 plus 10. I've got 16 plus 5. And then also 16 plus 6 here. 16 plus 6 there. 12 plus 10 is 22. 16 plus 5 is 21. 16 plus 6 also gives us 22. So clearly then, my early event time here is just simply 22. Perfect. So what we've done there then is completed the forward pass. So now we need to implement a backward pass. So to begin with here, you need to be aware then that for the sync node here, the early event time is the same as the late event time, or I should say the late event time is the same as the early event time. There we go. Correct way around. So 22 here is also my late event time. Now, what I'm going to do here is work backwards from the sync node towards the first node here, the source node, right? And don't forget then, when we're going backwards here, we're now finding the late event times. And for the late event times, we always want the smallest possible option, okay? So make sure you get that the right way around. So as you go forward, we want the largest possible option. As we go backwards, we want the smallest possible option, okay? So where do we begin here? So going backwards here, so we consider the late event times and the duration. Now clearly for this node here, my late event time must also be 16, right? 22 minus 6 would just give us 16 there, okay? I've only got that as my possible choice there, so that gives us the late event time for this node here, or this vertex here, whichever definition you prefer. So for this one here, again, I've got a choice of 2 now. So it's either going to be 22 minus 5, that would give us 17, or 16 minus 0. So clearly I choose 16 there as the smaller of those two options. What about this one here? So I've got a choice of 2 again. It's either going to be 22 minus 10, that would give us 12, or it's going to be 16 minus 3, and that would give us 13. So I'll just make a note here. So we choose the smallest then. So smallest of, so what are my choices again here? So 22 minus 10, 22 minus 10, or 16, so 16 here, minus 3. And again, don't forget here, we always choose the smallest, right? So 22 minus 10 is 12, 16 minus 3 is 13. So we choose 12 there as the late event time. Perfect. Okay. So we can now find this late event time here. So what would that be? So that is going to be a choice of 2 here. So my choices here then are, I've got 16 minus 4, so that would also give me 12, or 12 minus 0. Again, that would just give me 12. So clearly then, my late event time here is just 12. Nice and straightforward. What about this late event time here? So I've got a choice of 2 again here. So it's either going to be 12 minus 2, that would give me 10, or 12 minus 4. So the smallest option there is 12 minus 4, right? 8. So I input 8 there as my late event time. Right, and then finally to finish with here, for this late event time here, I've actually got a choice of 4. So let's just be very, very careful here. And I'll make a note just so it's clear then what we're actually doing here. So smallest of. So smallest of them. I've got 16 minus 4. 16 minus 4. I've got 16 minus 5. I've got 12 minus 5. And then finally here, 8 minus 0. So 8 minus 0. Well, clearly the smallest option there would be 12 minus 5, right? Which is 7. So we input 7 there, like so. And there we have it, right? We've completed the early and late event times here for each vertex or each node, again, whichever definition you prefer, okay? And there we have it then. So that gives the solution here to the one practice question for this video. And that just brings us to the end then of this video here on early and late event times.